So the purpose of this video is to explain the mechanism of action of a drug called digoxin, which is used in the treatment of heart failure and certain arrhythmias. Digoxin is a drug that inhibits the sodium-potassium ATPase that's found on the plasma membrane of all cells. And whenever it does this on the plasma membrane of the cardiomyocytes, it leads to an increase in intracellular calcium concentration and increased storage of calcium in the sarcoplasmic reticulum. And so because of this, during subsequent depolarization events, more calcium is released from the sarcoplasmic reticulum, leading to increased contractility. So digoxin has a fairly complicated mechanism of action, so it's nice to look at how it's working in sort of a schematic fashion. What I have shown here is a cardiomyocyte. Inside this cardiomyocyte is the sarcoplasmic reticulum, where calcium is stored. If we look at the molecular players, we have our sodium-potassium ATPase, which is maintaining low sodium concentration inside the cell. We have a sodium-calcium exchanger, which is using the energy stored in a sodium gradient to drive calcium against its concentration gradient, removing it from the cell. We have an L-type calcium channel, so this is a voltage-gated calcium channel. We have an ATP-driven calcium pump that's pumping calcium into the sarcoplasmic reticulum, and then finally a ryanodine receptor, which is a receptor for calcium. This releases calcium from the sarcoplasmic reticulum whenever there is calcium in the cytoplasm. So when an action potential travels down the cardiomyocyte, it results in opening of this L-type calcium channel. That allows calcium to flow down its concentration gradient into the cytosol. This calcium can bind to the ryanodine receptor, and when it does so, it triggers the release of calcium from the sarcoplasmic reticulum into the cytosol, and that's what's known as calcium-induced calcium release. So the calcium that enters the cytosol from both of these sources can bind to the contractile filaments inside the cell and induce muscle contraction. So after that happens, the muscle needs to relax, and the way it does that is by getting rid of this calcium from the cytosol, and there's two ways that this can be done. The first is that the calcium can be exchanged with sodium via the sodium-calcium exchanger, and that removes it to the outside of the cell, or it can be pumped into the sarcoplasmic reticulum via the ATP-driven calcium pump. So what happens in the presence of digoxin? Well, digoxin is binding to the sodium-potassium ATPase and blocking its function. And remember, this pump is what's responsible for keeping sodium low inside the cell and hence enabling the function of the sodium-calcium exchanger. When the sodium-potassium ATPase is inhibited, the sodium concentration inside the cell is higher, and that will lower the ability of the sodium-calcium exchanger to remove calcium because of this diminished sodium gradient. So instead of calcium being removed to the extracellular side, more of it is actually pumped into the sarcoplasmic reticulum. Because of this, you end up with increased calcium stores inside the sarcoplasmic reticulum. So how do these changes affect the contractility of the myocyte? Well, an action potential travels down the myocardium like it did before. That opens the L-type calcium channel, allowing calcium to flow inside the cell. And again, this calcium can bind to the ryanodine receptor, and that leads to calcium-induced calcium release. But now the key difference is, because of the fact that the calcium concentrations has become much higher inside the sarcoplasmic reticulum, you get a greater release of calcium from that organelle, and that leads to a greater concentration of calcium in the cytosol during systole, and that leads to a greater force of contraction. So the net result is increased calcium, increased muscle contraction, so the contractile state or the contractility of the heart has increased. So how does digoxin help in heart failure? Well, because of its effects on cytosolic calcium, it directly improves contractility, and this increases cardiac output, which is fixing the fundamental defect in heart failure. And this effect of the drug is known as its positive inotropic effect. Digoxin also reduces heart rate, and that's beneficial because it allows better ventricular filling and thus cardiac performance. And this is also the basis for the use of this drug in the treatment of atrial fibrillation. And I'll just mention quickly that this effect is also mediated via the sodium-potassium ATPase. It's just the effects there are due to a direct effect on the nervous system. And in patients with fluid overload, because you're pumping more blood out of the heart, you're also perfusing the kidney better, and so you're able to get rid of the excess fluid that accumulates in heart failure. So digoxin can also have a diuretic effect too in patients with heart failure, which is of course very beneficial.